how come we did not consider the stress caused by 100? I think we did, right? Oh, she said, never mind. Okay. Okay, never mind. You got it. Okay. So now, the x distance. Okay. What is this x distance? So x distance is running from left to right. Right? So that's why, remember, I told you guys, a lot of students make mistake with what is a x distance and what is a y distance. So the x distance, so BF, okay, BF, we got it as 166. Wait, let me go back. So BF 166. So we know that this is 166, right? So the x direction is 0.166. 166 divided by 2 minus by 75 times 10 to the power minus 3. Okay, because we are interested in this distance now. We're interested in this x distance now. Okay, so that's why it's important to know what is your x direction distance and what is your y direction distance. Okay, then the next case is plus our mx. So mx is a wait, let me see what's our mx. Mx is, wait, I'm looking for our mx value. Okay, mx is 22750. 22750. So you know that this is 22750, and the y distance is equal to d. So d is equal to, so let me look for my d. D is equal to 205. Okay, so 0.205 divided by 2 divide by IXX is 40.8. Okay, so 40.8 times 10 to the power minus 6. So this is equal to 100 power 3 divided by 5320 power minus 6. So it's equal to minus 18.797 times 10 to the power 6. Minus by 0.166 divided by 2 minus 75 power minus 3 times by 9600 divided by 9.03 power 9.03 power minus 6. So it's equal to 0.166 divided by 2 minus by 75 power minus 3 times by 9600 divided by 9.03 power minus 6. It's equal to 8.505 times 10 to the power minus times 10 to the power 6, then plus 22750 multiplied by 205 divided by 2 divided by 40.8 power minus 6 is equal to 57.154 times 10 to the power 6. So this is the, so once you've done that, it's all but just using your calculator. Okay, but the analysis is really, really important. Okay, so this will be equal to plus 29.852 times 10 to the power 6 Pascal. Okay, so if you look at the loading situation, right? So this is what we call eccentric. Okay, because we have eccentric, unsymmetrical loading. Okay, so this is based on the formula. Okay, so now where are we? Okay, so if I were to draw the element now, okay, so this is my y. Oh no, this will be my based on the orientation. So we have our x, y, and z. Okay, so if we were to draw element A, okay, we will draw element A. So this is our element A. So we calculated element A. We have 29.852 times 10 to the power 6 Pascal. Okay. So the next thing we know stress in X is equal to 0. We have nothing. Okay, we have nothing on stress in X for this case. The next thing we are going to do is we're going to find the shear. Okay, so what are all these shear? Okay, so this is shear in the plane intersecting the x-axis, right? And the direction is in our z, right? So for the other case, is shear the plane intersecting the z-axis, the direction is equal to x. Okay, so now we're going to identify what is our shear xz and what is our shear zx. So remember, to achieve equivalent, the shear xz is equal to the shear zx, sorry, is equal to our shear zx. Okay, so now we are going to, so for this case, we have two different direction about our shear stress or shear force, right? So we want to find the shear, okay, zx, right, generated or generate by Vx. Okay, so we also know that we have to apply thin wall analysis. Okay, we're going to apply thin wall analysis. So for this case, okay, we go, I need the cross-section view again. Okay, so the formula we're going to apply is shear, right? Shear Zx is equal to shear Xz, and this will be equal to Vx over Iyy, right? Qy divided by T, right? And what we are going to do is we are going to do thin wall analysis. And Q is equal to 1. Okay, this is because it is white flange. For this view, okay, this is white flange. Okay, so now we know that if this is my XX direction, this is my Vx. And we know that the Vx is equal to 16,000 Newton. Okay, and then we know this is how the shear flow move. Right, and then over here, this is this is our element A. Okay, so the distance from here to here is 75 millimeters. Right, so we are going to look at this area. All right, so it makes sense. What do I mean by it makes sense? So okay, we know what is our Vx, yes, right? We also know what is our Iyy. Listen, give me another 5 minutes, okay? I've been told not to go over time by the chair, okay? So I will not go over time. I know I'm already over. Just give me a bit more time. So this is 9.103, right? So that's why I keep on emphasizing follow the orientation as what this says, okay? That's the important bit. So 9.103. Okay, 9.103. No, 9.03. It is 9.03 times 10 to the power minus 6, right? Meter to the power 4. And then we know the T, the thickness is the what? The thickness is this thickness, which is equal to our TF. Okay, so TF is equal to what? TF, sorry for jumping here and there, okay? TF is equal to 11.8 times 10 to the power minus 3. Okay, so this is 11.8 times 10 to the power minus 3 meter. Okay, so 11.8. Okay, so the next thing is we want to find Qy. So once again, the most headache one is Qy. Okay, so Qy means first moment of area about the y-axis. So now the area is rotating about the what? Y-axis, right? So this axis is the fixed axis now. Okay, so if I were to write the formula, so it's equal to QY multiplied by the area X bar. Why X bar? Because this distance from here to here is your what? Is your X bar. Yes or no? It's not your Y bar, it's your X. Now, this is another stage where a lot of students make mistake, and I don't want you all to make mistake. Just remember, if Q is Y, the distance is X. Or if Q is X, the distance is what? Y. Okay. So from here, okay, so from here, so again, parallel to the axis is my depth. Okay, perpendicular is my width. Okay, so for this case, my width will be 11.8, right? 11.8 times 10 to the power minus 3, right? The area is 75 times 10 to the power minus 3. And then the distance is equal to BF. What is my BF? 0.166 divided by 2 minus by 75, 0.075 divided by 2. So we are finding this X bar distance, okay? So this will be equal to 0.166 divided by 2 minus 0.075 divided by 2 times by 75 power minus 3 times by 11.8 power minus 3. Okay, so this is equal to 40.268 times 10 to the power minus 6 meter cube. Okay, so therefore the shear ZX at point A, at element A, is equal to 16,000, right? Multiply by or divide by 9.03 times 10 to the power minus 6. Okay, and then we have 40.268 times 10 to the power minus 6, and then divide by thickness 11.8 times 10 to the power minus 3. We don't need to divide by 2 because our analysis is based on white flange. So this will be equal to 16,000. 268 power minus 6 divided by 9.03 power minus 6 divided by 11.8 power minus 3. So this is equal to 6.047 times 10 to the power 6 Pascal. Okay, I'm going to stop here now. Okay, I will post homework probably tomorrow. Okay, and if that's the case, thank you for your attention. And I know I went over time. Okay, I apologize for that. With that, I'm going to stop recording.